you will also be able to learn the techniques like how to apply one sample t-test, then two sample t-test, pair t-test. And once the t-test is over, then we will move on to one-way ANOVA and two-way ANOVA. That will also be discussed. And after that, we will also discuss your cluster analysis part and chi-square. Chi-square is a non-parametric test. So first I'll discuss about parametric and non-parametric a little bit. Of course, non-parametric I am not covering, but chi-square definitely is one of the non-parametric tests which I'll cover. And if you have any question at any time point, you are most welcome to ask me, right? Okay, let me share the presentation and start with the proceedings. Just wait for a moment. Can you see my desktop? Is this visible? Yes, anyone, please?
Yes, sir.
Okay, all right. So because it's important to discuss the theoretical part before coming to the practical part. This correlation regression we have already discussed in detail yesterday. And today we'll start with the more important part, that's called estimation and testing of hypothesis. Can you see this slide on estimation and testing of hypothesis?
Yes, sir.
Yes,
Yeah,
sir.
okay. So we'll mainly discuss here the parametric test. And there are certain assumptions of the parametric test. Because I'm not covering the non-parametric, maybe somebody else will cover. So estimation and testing of hypothesis. So there are three terms here. One is estimation, another is testing, and the third one is hypothesis. So I'll explain you the meaning of all the three. What do you mean by estimation? What do you mean by hypothesis? What do you mean by testing? So try to be attentive because this part is very, very important, and generally it is not covered in detail in many of the books, and students or participants generally get confused about many different terminology of estimation and testing of hypothesis. Okay, so these are also called tests of significance. Now, what are these tests of significance? See, there is always some kind of population. It's very difficult to study the entire population. Now, for example, in our student, if you see in Punjab University, Chandigarh, we have around 22,000 students. 22,000 students. If somebody give me a very simple task that you have to find out the mean height of all the students. Now, even this simple experiment you cannot do with such a large population. Why? Because you move to one department, 5 students are absent. You go to another department, 10 students are absent. You go to another department, another 8 students are absent. So obviously you cannot have even a population. It's very difficult to study a population of 22,000 people. But let's say I take a sample of size 500. So if there are 50 departments, I go to each and every department and take a random sample of 10 from each and every department. So you will get this random sample of 500. So 500 sample size can be easily taken, while 22,000 people difficult to study. So there is always some kind of population which is difficult to study. So what we do, we take out a sample from this population, and generally we take a random sample. Now, what is the meaning of this word random? Random basically stands for that there is no favoritism, there is no biasness, right? There is no favoritism, there is no biasness. Here I have written the definition of the randomness. Random, every member of the population, if every member of the population has the same chance of being selected into the sample, then it is called a random sample. Same chance for everyone. For example, if there are 30 students in the class and somebody give me this task that you have to select 5 students. So it may be possible that I know the name of 5 students, and if I go by the name selection, there may be favoritism, there may be biasness involved. Hopefully you understand what I'm trying to say, right? The better way is that I can write the name of each and everyone on a piece of paper, fold it, mix them thoroughly, right? And put into the container and then select one person at random. Whosoever name appears, that person is selected at random, right? So this is what we mean by the word random, because anybody is having an equal chance. So this is what we mean by random. So we generally take a random sample from the population. Now, there are two things. Please try to understand. There are values which are concerned with the population, and there are values which are concerned with the sample. Suppose your population is having 1 lakh people. You take a sample of size 500, x1, x2, x500. Now, based on these sample observations, because they are relating to height, they are relating to weight, they are relating to BMI, they are relating to anything else, right? IQ, etc. I can always compute mean. You add 500 observation, divide by 500, you will get mean. Similarly, for 500 observation, you can compute variance. And same way in 500 sample, you can look at how many males are there, how many females are there. That is called proportion. Proportion of males and proportion of females. So from the sample observations, we can compute sample mean. We can also compute sample variance. We can also compute sample proportion, like how many males are there, how many females are there, right? Now, these are the values which will be known to you after collecting the sample. X bar will be known to you, S square will be known to you, small p will be known to you. And if your values are associated with the sample, then it is called a statistic. Let me just repeat. If your values are concerned with the sample, then it is called a statistic. For example, X bar is a statistic. Small s square is a statistic. Small p is a statistic. And there are values also concerned with the population. If your values are concerned with the population, then these values are generally unknown. Then these are known as parameters. For example, there is a population mean. There is a standard notation for population mean in statistics. Please remember this. We call this as mu. Mu. Mu is called mu. Similarly, standard notation for variance, we call this as population variance, sigma square. Then population proportion. Population proportion is capital P. That means in the entire population, how many males, how many females are there? That is this. Now, these parameters are generally unknown because it is difficult to study the entire population. But what we can do? What is the entire crux of statistical estimation? The entire crux of statistical estimation is to estimate the parameters of the population based on the sample. Is to estimate the parameters of the population based on the sample, right? Hopefully, so if you have taken an appropriate sample size, if you have used the appropriate sampling technique, what you will expect? If there is the appropriate sample size, appropriate sampling technique, then what you will expect? You will expect that this sample mean, which is X bar, which you have computed, will be closer to this population mean mu. Or you can say that X bar will be an estimate of this population mean mu. Similarly, this S square, which is called sample variance, will be an estimate of the population variance, sigma square. Similarly, this small p, which is called sample proportion, will be an estimate of the population proportion, which is called capital P. Hopefully, you will agree with me. So we are moving backward from sample to the population, that these parameters can be estimated based on the sample observation. So we are referring back to the population, and this problem is basically called estimation. X bar is an estimate of mu. S square is an estimate of sigma square. Small p is an estimate of capital P, right? So we are trying to estimate the parameters of the population based on the sample, and this is basically called statistical estimation. Hopefully this part is clear. Yes, please. Is this clear?
Yes, sir.
Anybody?
Yes, sir.
Right. Now the next question, because there were 3 words. One was estimation, which I have explained you. Another was testing, and then hypothesis. Now, how will you come to know that X bar is closer to mu? Because mu is unknown. How you will come to know that S square is closer to sigma square? Of course, if you have some information and you say that X bar is closer to mu, then your estimate will be good. If S square is closer to sigma square, estimate will be good. So the next question comes, we need to test it. How far they are, how close they are. If they are close to each other, that means they clear the test of our hypothesis, right? So we need to test further. How close is X bar closer to the mu? How sigma square is closer to S square, and so on. All right. So for that purpose, we need to test it. Now, before testing, what we need to test, we need to define certain hypotheses. We need to define certain hypotheses. So I will take you how to define hypothesis, and then we will see how to test the hypothesis, right? Now, before coming to the defining of the hypothesis, null and alternative hypothesis, question is how to take out a sample from the population. How to take out a sample from the population is based on a technique which is called sampling techniques. Of course, I don't have time to discuss all these sampling techniques. There are various sampling techniques: simple random sampling, with replacement, without replacement, stratified sampling, cluster sampling, probability proportional to size sampling, judgment sampling, purposive sampling. Many sampling techniques are there. So some of them I have listed. So in different situations they are used. For example, the first two sampling techniques, simple random sampling, with replacement, without replacement, they are generally used when the population is more or less homogeneous in nature. If population is more or less homogeneous in nature, then we use simple random sampling. What do you mean by homogeneous? Homogeneous means that they belong to the same group. They are having certain similar characteristics. For example, if I go to 10th class in a school, if I move to 10th class, one of the section, then I'll assume that all these students, they are of the same age group. They are reading the same material. Same teacher is teaching them. So this group can be considered as an homogeneous population. Hopefully you understand. So simple random samplings are generally helpful when population is more or less homogeneous in nature. Then you can apply this technique. Then there is a stratified random sampling, but population is not necessarily homogeneous always. It may be heterogeneous also. For example, if somebody give me this task that you have to get the assessment of the health in the entire Haryana state, right? Now in or West Bengal state. In West Bengal state, there are certain remote areas. There are certain posh locality areas, like one of them is Calcutta, main Calcutta. Then you have Vishwabharati, Shanti Niketan. All these are certain good locality areas. Bardhaman and all these are good areas where there are a lot of hospitals, facilities available, right? But there are certain remote areas also near Diga or somewhere where I have gone in Calcutta, right? So obviously, these population cannot be considered as a homogeneous population. There are certain remote areas where health facilities are not available. There are certain hospitals like Calcutta where good facilities are available. So I want to assess what is the status of the health in the entire West Bengal, right? So it's not I cannot use simple random sampling because population is not homogeneous. So in such cases, we divide the entire population into different stratas. For example, in dividing the West Bengal, one district can be considered as one strata, with the assumption that within this district, within a particular district, the health facilities will be almost similar for all. And if there is a variability will be between the districts. Between the districts, they may differ, right? So in such type of situations, and then I take out a sample from each and every strata. That means I take a sample of size, let's say 300, 400 from each and every strata. So if there are 20 districts, I'll take a sample of size, let's say 50 from each. So I'll get a sample of size 1000 from 50 from each, 20 districts. So I'll get a sample of size 500. But this is representing the entire West Bengal. So for that purpose, we use this, what is called stratified random sampling. Then, stratified random sampling is used when the population is not homogeneous, it is heterogeneous. Similarly, there is a quota sampling. Quota sampling is not a probability sampling. It's based on certain fixed quotas. For example, when there is admission policy, certain fixed quotas are there. 5% defense, 5% defense quota, 15% for SC/ST category, right? Then 2% for handicapped people, 60% in general. So then you take a sample of size according to the fixed quota. You cannot take more than 5% for defense. You cannot take more than 50% for 15% for ST/ST category. So for that purpose, we use this what is called quota sampling. Similarly, the purposive sampling is also sometimes useful. Systematic sampling is used for large sample surveys. And when the statas are not of equal size, then we use probability proportional to size sampling. And sometimes in medical sciences, in economics, cluster sampling is also useful. So you have to go through the entire sampling techniques, where to use which type of sampling. There is a multi-stage sampling, two-stage sampling, single-stage sampling, three-stage sampling. Many sampling techniques are there. And for that, I'll recommend a book where you are sitting right now at the A.K. Goon Gupta Center. So they have written a very good book, Fundamentals of Statistics, Volume 2, by M.K. Gupta and A.K. Gupta, M.K. Das and A.K. Gupta. This center is basically after the name of A.K. Gupta, right? So you can go through his book. The book name is Fundamentals of Statistics, Volume 2. So you will see all the sampling techniques, and they have given with examples where to use which type of sampling techniques. Because my lecture is not concerning with sampling techniques, so I'll skip this part. I have given you some idea that in certain situations, we have to choose the appropriate sampling technique. Not only appropriate sampling technique, but also there are methods to compute sample size, right? Every day I am computing sample size for doctors, and I generally take 2 days workshop only on computing sample size in medical research. So if you have an appropriate sample size, if you have used the appropriate sampling technique, you will expect and you will really appreciate that your sample estimates even sometimes better than the entire population, right? Okay. But here I'll give you some idea about the sample versus population. What do you mean by sample versus population? Actually, you take out a sample from the population in such a way so that it should represent the entire population. It should represent the entire population. Whenever we go to a market to buy, let's say, grapes, this is what the people usually do. They pick up one, then they taste it. If it sounds good, they buy it, and sometimes they leave it. And sometimes they leave it, right? Now, if you ask a statistician, he will go one step ahead. He will pick up one from here, one more from here, possibly one more from here. Why? Because we are looking for a representative sample. Because what happens sometimes if you are taking from one corner, sometimes the good ones are always at the top and bad ones are hidden behind. And if you take a sample from one corner, you will not get a very good estimate, right? So that is the idea of sample versus population. It should represent your entire population. But in this case, you have to be very careful, provided the person in front of you, who is the owner of this grapes, will allow you to do this. Okay. Here is another peculiar example of sample versus population. There was very senior doctor, and he was teaching the importance of sampling techniques to the junior doctors. Try to understand the theory in this story, please. Very senior doctor was teaching the importance of sampling techniques to junior doctors. And one of the junior doctor didn't get convinced. He says, "Sir, why to look at the sample? Why not to study the entire population?" And then the senior doctor was wise enough, and he took this junior doctor to the nearby patient, and here is the patient, and asked this junior doctor that you take out the entire blood of this patient. The junior doctor said, "Sir, patient will die." Then the senior doctor asked him, "What you will do?" He says, "I'll take a sample." You follow my point? So you cannot study the entire population. You cannot take out the entire blood of the patient. Patient will die. Then what we do? If somebody is having a stomach pain and you are going to a doctor, doctor will not cut the stomach and see what is inside. He will prescribe you a certain blood test or maybe ultrasound. Whenever we give blood test, We give a sample, not our entire blood of the body. This is what we mean by, and that sample of blood representing the entire blood of our body. That is, our body is a population. And that 5 ml or 10 ml is a sample. You understand what I'm saying, hopefully? Yes, please. You understand? Hello?
Yes, sir.
So sample versus population is a very, very important topic. Now, what is a representative sample? Why I say it should represent the entire population? Look at the definition. A sample that represents the characteristics of the population as closely as possible. A sample that represents the characteristics of the population as closely as possible. So here you can see a target population. Here is a representative sample. So this is a picture of a kangaroo. There is a baby of kangaroo. So here you can say that baby represents the entire characteristics of the mother. So can be considered as a representative sample. It is having similar properties. But if I replace this baby with a baby of a dog or a cat, do you think it will be a representative sample? It won't be a representative sample there. This is what we mean by representative sample, that it should represent the characteristics of the population as closely as possible. That's called a representative sample. All right. So with this background, now you have some idea what do you mean by sample, what do you mean by population, what do you mean by estimation. We will go through certain learning objectives in this lecture. We'll understand. Yes, please.
Sir, I want to know what should be the sample size. If we have a large amount of population, then what will be the size? Or I can say what will be the percentage of sample when we select from the population, if we have a large population.
Yeah.
Heterogeneous population.
Yeah. See, population, taking a sample from the population doesn't depend upon percentage. First of all, try to understand. I cannot say you take 2%, you take 5%. For example, if I give you that you study the entire health status of India, and even simple exercise, you take 1% people. 1% will come to 1.5 crore people. Do you think it's easy? Even percentage we cannot talk about whenever we talk in the sample size. So for calculation of sample size, there are more than 200 formulas. They are used in different situations. For example, let's say there is certain disease, and this disease has a prevalence rate of 5%. That means out of 100 people, 5 are affected. Then I can compute the sample size. Sample size is also based on the incidence. What is the incidence of certain disease? Sample size is also based on the previous studies. Somebody has conducted the study. So from that study, I can go for the let's say it's a comparison of 2 control and experimental group. And somebody has done the experiment already. So I can use their mean and standard deviation to compute sample size. If there is no study, then we can do our pilot study of 25 to 30 people and go for a computing of mean and SD, and then compute the sample size. Sample size can also be computed based on the risk ratio, odds ratio. It can also be based on confidence interval. So most of the information has to come from the respondent. Whenever doctors, they come to me, I just look at their problem and ask them certain questions that you have to answer these questions, that what is the prevalence rate of the study, or if prevalence is not available, what is your confidence intervals, is there any previous study or not, and they provide me the information. And when the information is with me, then I use the appropriate formula, because if they provide me information in terms of, say, risk ratio, then I'll use risk ratio formula. If they provide information in terms of prevalence of certain disease, then there is a different formula. If they provide information in terms of odds ratio, then there is a different formula, right? So if you see my book on medical statistics, I have one complete chapter, then in which type of situation, which formula to be used. So there I have make use of 8 to 10 important formulas, which generally cover 80 to 90% of the computation of the sample size. So you can go through that book, on medical statistics, you will come to know how to compute sample size. You follow my point? It's not a straightforward that you take 2% or 5%. It's not like that. Yes, please. Is that idea?
Thank you.
Is clear? Okay.
Yes, sir.
So these are going to be the learning objective here, to understand the role of significance test, to distinguish between null and alternative hypothesis, critical region and level of significance, interpretation of p-value, type 1 and type 2 errors. So all these things now I will discuss. First, what do you mean by hypothesis? Now, in many of the books I have, substandard books, I have also seen that they say negative hypothesis, they say positive hypothesis. Remember, in statistics, there is no concept of negative and positive hypothesis at all. What is an hypothesis? Read the definition. A tentative statement regarding the population, not regarding the sample. A tentative statement regarding the population, relating to a certain phenomena. Relating to a certain phenomena means relating to height, relating to weight, relating to IQ, relating to BMI, in which the researcher is interested and wants to verify on the basis of the sample. That is the definition of the hypothesis. The idea here is, if you are planning certain study, right, then obviously you will having certain objectives, and for each objectives there is going to be hypothesis. For each objective, if there are 5 objectives of your study, there will be 5 hypotheses, null as well as alternative hypothesis. But this is the basic definition of hypothesis. Hypothesis stands for that if you can frame the objectives of your study into 1 or 2 sentences, that becomes basically the hypothesis, right? Then there is a concept of null and alternative hypothesis. Now I'll skip this slide. I'll take it with the help of example. Look at this example. Let's say somebody is interested to test that I can expect, that is his claim, his or her claim, that I can expect that the mean IQ means intelligence quotient, that mean IQ of this population is likely to be 100 because they are average type of people, and mean IQ of this population will be around 100 or it will be close to 100. That is the he's presuming, right? So whatever they are presuming or whatever they want to test, we always write down under H0. Try to understand, please. Whatever they presume, whatever their assumption that this is likely to be this, we always put that aspect under H0. H0 stands for null hypothesis, denoted by H0. H0 or H0 we call this. So here I'm referring to mean. And what is the parameter of mean in the population? Mu. So I'll be using that notation now, that mu will be equal to 100. So my simple null hypothesis will be that mean of the population is equal to 100, right? That is what the person's claim is. Whatever the claim, you put under H0. Okay. And under H0, please remember, listen to me carefully. Under H0, there is always equal to sign. In many of the substandard books, people write under H0 not equal to sign, sometimes greater than sign, sometimes less than sign. Absolutely wrong, absolutely absurd. I will prove it today. So under H0, there is always equal to sign, equal to whatever you are. If there is certain benchmark, for example, if it is not relating to IQ, if it is relating to, that the mean, this is my claim, that the mean height of all the university students should be around 160 centimeter. So my hypothesis will be that mu is equal to 160 centimeter. If it is relating to that BMI of all the university students must be around 24. So I'll say mu is equal to 24. Now it is not necessary you always test mean. You could be testing variance also. So if you are testing variance, then hypothesis will change. Somebody can frame this hypothesis that variance of this population is likely to be around 5. Then hypothesis will change. Now they are referring to variance. And what is the parameter of variance? If you see, recall, this was the parameter of variance. What is the parameter of variance? Sigma square. Right? This is the parameter of the proportion. Since they were referring to mean, so I have used mu. Now I am referring to variance. So I'll frame the hypothesis that sigma square equal to 5. So accordingly, I will change immediately. Accordingly, I'll change immediately the hypothesis. You follow, hopefully you follow my point. Similarly, let's say there could be two populations also. I want to compare them. Let's say one is a government school population, another is a convent school population, and I want to compare the performances, that the performance of both the schools are same. So performance of both the schools will be same. If the mean scores of both the schools are same, obviously their performances are almost equal then. So if mu1 denotes the mean of the government school population mean, and mu2 denotes that of the convent school, so under H0, I will test mu1 is equal to mu2. That means when I say mu1 is equal to mu2, that means performance of both the schools is same, right? So this is how we frame null hypothesis. Okay. So in null hypothesis, there is always equal. Similarly, if somebody claimed that in this population, 40% of the population is likely to vote for this party. So I am referring to proportion now. So my hypothesis will change. I'll write capital P is equal to 0.40. 0.40 means 40%. So accordingly, depending upon the problem, depending upon the study, you need to frame your null hypothesis. Whatever is the claim, put under H0. Now, this is what you are presuming. Now, this assumption may not be true. So there are alternative hypotheses. Null hypothesis is always one, but null hypothesis could be many, depending upon the research problem. Let's say somebody has this claim that these are very, very good students. I can give you 100% bet that the mean IQ of these students are definitely going to be more than 100. Then alternative hypothesis. Under H0, you will always write that mu is equal to 100, but alternative will be that mu greater than 100, because person is claiming, right? Person is claiming that this is a very good population. Their mean IQ will be more than 100, right? Now, it may not, if you're under H0, you write mu is equal to 100. It may not be equal to 100. It may not be, because you don't know what will happen in the population. So simplest alternative is, which is denoted by H1 or HA, we write mu not equal to 100. Now, if I write mu not equal to 100, then it could be less than 100. It could also be more than 100, right? And that's why this type of alternative is called two-sided alternative. Two-sided means I'm not sure. It could be less, it could be more. I'm simply testing for not equal to. That's all, right? So that is one of the alternative. But if somebody is 100% sure, very good students, their mean IQ, I'm sure it's going to be more than 100. Then H0 will remain the same, but alternative will change. Alternative will be mu greater than 100. Similarly, if somebody is 100% sure, these are very dull students, they don't know anything, their mean IQ cannot be 100, it is definitely going to be less than 100, alternative will change. Then you are writing alternative as mu less than 100. Now, this is greater than 100, this is less than 100. This is also one-sided, because greater means on the right-hand side, less means on the left-hand side, right? So that means both of them are one-sided. To distinguish between greater, we write one-sided right tail. And for left, less than, we write one-sided but left tail. Okay. Now, where to use one-sided, where to use two-sided? People get confused here also. Let me explain you clearly. In 70 to 80% of the cases, we use two-sided alternative. Why? Because we don't know what will happen in the population. We don't have any idea. One-sided is to be used only when somebody is 100% sure that this is likely to happen in the population. It is greater or less. Then you use one-sided. Even if you are 100% sure, even if you are 99% sure, 95% sure, do not use one-sided. Then you use two-sided. Let me give you an example of one-sided. People are suffering from blood pressure. Let's say they are going to a doctor. There are 20 patients who are suffering from low BP problem, LBP, low blood pressure. Okay. Now there are standard medicines available in the market. People are using for the last 20, 30 years. Very well-known medicines for controlling blood pressure. And doctor put them on these medications, that you take these medications for 2 months. and come after 2 months. Now, these are very well tested medicines people are using for the last so many years. Clinical trials have been done. So what the doctors will expect next time? The doctor's expectation will be that these low BP patients, now they should come back to normal, right? So he'll expect if their low BP problem was there, then it should be greater than normal, greater than that point, initial point. So in that case, we use one-sided. Hopefully the difference between one-sided and two-sided is clear to you. Okay. Now, once we have written the null hypothesis, the alternative hypothesis, then question is, what are these type 1 and type 2 errors? People generally talk in statistics, right? Look at what is written in green line. No study is perfect. No study is perfect. There are always chances of errors. Let's say I take a basket of 100 oranges. Do you think all of them are going to be of the same and a good quality? Not necessary. You can expect few pieces to be of bad quality, right? No, let's say I buy 100 shirts or 100 suits. You cannot expect that all of them are going to be good quality. Some of them may be of bad quality also. Some of them. So there are always chances of error. I'm talking of even in any manufacturing process. If let's say 500 items or 1000 items are produced, all of them are not going to be of the same quality. Although they are coming from the same material, same machine, same person is operating, but there will be little bit of variation, which is beyond your control, right? Now, obviously, no study is perfect. There are always chances of errors. And in statistics, generally, these errors are called type 1 and type 2 errors. Very serious errors. Now you know what is H0, what is alternative hypothesis. So here is look at this table and try to read like this. Decision, here H0 true, H0 false. So your decision is reject H0 when H0 is true. What does this mean? H0 is true means something is of good quality, but it has been rejected. Something is of good quality, but it has been rejected. That means it is an error. Something was of good quality, it has been rejected. That means it is an error. And this type of error is called type 1 error. This type 1 error generally happens. This type 1 error generally happens in selection procedures. Let's say there is a selection of the candidates for assistant professor, associate professors, and there are certain errors. It happens that there is a good candidate having good number of publications, good number of conferences attended, something, each and every parameter is okay. But there is another candidate who is having little bit of pull and push. So rather than selecting the better one, they have selected it because they reject the better one and select the next one. That's called type 1 error. And then the institute has to suffer for how many years? 30, 35 years. That would planted for 35 years. And there are samples in our university, maybe in your university also, you might have seen. That is the result of type 1 error. Very, very serious error. It has been committed right there in the beginning, right? So reject H0 when H0 is true. Something was of good quality, but it has been rejected. Somebody else has been selected, type 1 error, right? What is type 2 error? Type 2 error is accept H0 when H0 is false. Something is of bad quality and you are accepting that. Again, it is an error. And this is called type 2 error. This is called type 2 error. Now, let's say I give you an example of type 2 error. Let's say I want to buy apples. And there are bulk of apples lying over there. I can see from my eye, they are not of good quality. But the owner of the apple says, sir, you have to take only 1 kg. You just pick and choose. Use your judgment. So I just use the trick of pick and choosing. Pick and choose and bring 1 kg at home and consume them. The entire family consume and we got food poisoning because we accepted a bad lot. 2-3 people are admitted in the hospital. Doctor charged me 15,000 rupees. Whose loss is this? My loss, because I accepted the bad lot. That's type 2 error. accept H0 when H0 is false. That's type 2 error. I'll give you few more examples of type 1 and type 2 error so that you should not get confused. What should have been the correct decision? Correct decision is reject H0 when H0 is false. Something is of bad quality, you also reject it, that's the correct decision. Another correct decision, accept H0 when H0 is true. Something is of good quality, you also accepted that, that's the correct decision. So these diagonals are type 1 and type 2 errors, and off diagonals, they are correct decisions. That is the idea of type 1 and type 2 errors. Now these are errors. We want these errors to be maximum or minimum? Obviously, we want these errors to be minimum because errors has to be minimum for a better result, right? The more the error, worse is the result. Okay, so let's try to understand. Now I'll pick up another few examples of type 1 and type 2 error. Look at type 1 error and type 2 error from medical point of view. Medical people generally they call type 1 error as false positive. What do you mean by false positive? The person does not have the disease, but the test says they do have. When COVID-19 appears right there in the beginning, 2020, there was no proper testing. And when there was no proper testing, people diagnosed with the wrong disease. They don't have any disease, but the test says that they do have. Now, where this will go? This will be put into the hospital with another patients, those who are already suffering. And he was not having, but he will dwell COVID-19 because type 1 error has been committed or false positive. And let me tell you, I was involved in COVID-19 research, and right in the beginning, when there was no proper testing, about 30 to 40% there were false positive cases. You cannot think of even, right? Look at the court example. Convicting an innocent person. The person doesn't have done any crime, but he has been convicted by the court. That's type 1 error. Very, very serious error. Look at type 2 error. A false positive. Type 2 error is called false negative. Look at this thing. The person has the disease. Person is having COVID-19, but the test does not pick it up. Test says they don't have. Now this person will come home. There are 5 members in the family. All of them will be affected. Why? Because false negative case. Type 2 error. Look at the court example. Not convicting the guilty. The person has done a crime, but the judge has let him go. He may kill a lot of other people. Not convicting the guilty. That's type 2 error. So these are the examples from medical test, example from court. You can also read this one, right? So hopefully the idea about type 1 error, type 2 error is clear to you. I have given you many examples. Now we move on to very important concept that is called level of significance. Level of significance is nothing but probability of type 1 error. There is type 1 error. It may be 2%, it may be 5%. So if you look at the probability of this event, that is basically called level of significance. And generally denoted in statistics, we call this as alpha. You must have seen in the research papers, we take alpha to be 5%. We take alpha to be 1%. Why not take alpha 50%? Why not take alpha 10%? Because we want probability of type 1 error to be very, very small. Now, what do we mean by this level? Level of significance. Level of significance basically denote that you cannot go beyond this level. Try to understand, please. These things are not clearly written in any book, but if you are with me, you will be able to follow. What do you mean by level of significance? That means you cannot go beyond this level. Let me give you an example of level of significance. Suppose there is a basket, and in basket there are 100 apples, right? And out of that, 2 or 3 are bad pieces. Rest of them are okay. So I'll accept that lot. Okay, it's fine. I'll accept that lot. But there must be some limit. Let's say another basket, there are 100 apples, 40 are bad quality, 60 are good quality. Will you accept that lot? You will not accept, you will never accept that lot. Why? Because it is beyond your controlling level. What is the controlling level in statistics? Maximum allowable error in statistics is 5%. What does this mean? This basically means that if out of the 100 items, up to five, maximum up to 5, even are of bad quality, still I can accept that lot. But if it is below, if it is above 5, say 10%, 15%, 20%, I will straight away reject the lot. This is what do you mean by alpha, or the level of significance. Remember, whenever we are involved in testing of hypothesis problem, we design certain questionnaire, there are objectives, there is a study. We fix our alpha even before conducting the experiment. That I will take alpha to be 5%. I'll take alpha if it's a very, very sensitive experiment. If it's a very, very sensitive experiment, I cannot afford even 5%. I have to take alpha to be very, very less. For example, if your experiment is concerning about testing of aeroplanes, and I take alpha to be 5%, what does this mean? That means if 100 aeroplanes will fly, 5 of them are likely to fall. Who will sit in the aeroplane next day? Nobody will sit in the aeroplane. There are air accidents, but very rare. So there you need, in such type of sensitive experiment, you need alpha to be very, very low. Maybe 1 in 1 lakh, maybe 1 in 2 lakh, something like that. Okay. So there you need alpha to be 0.00001. So that it's very, very less. So depending upon the research problem, we fix our level of significance. Okay. Hopefully the level of significance is clear. Then there is beta. Beta is basically called, alpha is called probability of type 1 error. Beta is called probability of type 2 error. Beta is called probability of type 2 error. But beta as such is not important. But 1 minus beta becomes important. 1 minus beta basically denotes the power of the test. Power of the test. So power of the test is directly related to the sample size. It is also related to your sampling technique. And sometimes there are objections. Whenever we are writing a research paper, let's say I take a sample of size of 10 people only, and I am giving the inference about the entire population. And then I apply t-test or z-test or any other test. And then the referee asks me this question, or the editor asks me this question: what was the power of this test? And when I computed the power, it was just 40%, because I have not taken the appropriate sample size. So 1 minus beta is more important because it is directly related to your sample size. It is directly related to your sampling technique. Let's say my population was heterogeneous and I have used simple random sampling, which was absolutely wrong. So you are coming out with the wrong estimates. And if you come out with the wrong estimates, everything will collapse. Your estimates will be totally wrong. You are committing type 2 error. Power of the test will be very, very low. So this is what do you mean by beta. This is what do you mean by alpha. Now, then there is a concept of what is called p-value. Now, alpha is fixed in advance. P-value is nothing but the area outside the computed value. For any statistics, we compute the value. And then there is a graph for every statistics. Graph for t distribution, graph for normal distribution, graph for chi-square distribution, graph for f distribution. And p-value, we compute the value of chi-square, we compute the value of t, we compute the value of z. What is the p-value? P-value is nothing but area outside your computed value. So I'll explain you this thing. Just wait for a moment. But for the time being, you remember that we reject H0 if P is less than alpha. Yesterday, I told you a number of times. We reject H0 if your P value is less than alpha. Alpha is fixed in advance. Suppose your P value is 0.002, which have been given by the test statistics. Your alpha is 0.05. So you will reject the null hypothesis. You will reject the null hypothesis because P is less than alpha. When P is more than alpha, we do not reject H0. Alternative will be accepted. right? So this is the concept of p-value. P-value is nothing but area outside the computed value. Let's say I fix my alpha to be 0.05 and my alternative hypothesis is two-sided. So this is an error. Probability of type 1 error is 5%. So if I'm testing mu is equal to mu naught against mu not equal to mu naught, so it's two-sided. I don't know whether mu is less than mu naught or mu is greater than mu naught. So obviously this error will also be distributed equally on the left hand side, equally on the right hand side. So if it is a 5% error, I divide this by 2. I'll take alpha by 2 on the left hand side, alpha by 2 on the right hand side, and that is this green area. So alpha by 2 of 5% divided by 2 will be 2.5%. So this green area covers 2.5% on this side and 2.5% on this side. Right? Now, everybody knows about the standard normal table. We know about the standard normal table. And in standard normal table, if you remember, if you know about the standard normal tables, there are, if I take alpha to be 0.05, and from table I can compute the critical point. If you know the probability, you can compute point. And corresponding to 0.025, corresponding to here 0.025, if you compute that point, it will come out to be 1.96. And there is no need to compute on the left hand side because this will be minus 1.96 because it's a symmetrical graph, right? So for alpha to be 0.05, the critical points are defined by minus 1.96 and 1.96. Now, what is the p-value? If let's say your exact computed value is coming out to be 1.96, exact computed value is 1.96, right? If your exact computed value is 1.96, then look at the definition. P-value is nothing but area outside the computed value. So area outside this is 0.025, area outside this is 0.025. So it will be 0.025 plus 0.05. Your exact p-value will be 0.05. But suppose my computed value is greater than 1.95. Suppose it is 2.31. So this is 1.96. So 2.31 will come somewhere here. You see, this is 0, then 1. This is 1.96. 2.30 will come somewhere here. Similarly, minus 2.0. And p-value will be area outside that region. I'll again put 2 bars here, 1 bar here, 1 bar here, and look at the area outside. So area will become small. Smaller the area, it will go to the chances of getting into the green region. Green region is your rejection region. That's also called critical region. So smaller the p-value, greater is the chances that your hypothesis will be rejected, right? And same way opposite. Suppose your computed value is 1.25. 1.25 will come somewhere here. Then I'll put a line here. I'll also minus 1.25, I'll put a line here. Then area outside this will be p-value, then area will increase. Once area will increase, it will cross this boundary of critical region. It will fall into the acceptance region because white region is acceptance region. So you cannot reject your H0. You cannot reject H0. This is what I have written. So, however, if your computed value is 1.25, the p-value will be more than 0.05 and it will fall into acceptance region. That means white region. Therefore, we cannot reject H0. So this white region is acceptance region, green region is rejection region. What does this mean basically? Simple idea is, if you don't understand anything, smaller the p-value, greater is the evidence against null hypothesis. Here's the last line you see. Smaller the p-value, greater is the evidence against null hypothesis. If your p-value will be very, very small, that means it is definitely going into the green region. And it is a rejection region. You will reject your hypothesis. But if p-value is higher, when p-value will be higher? When computed value will be low. So there is an inverse relationship between computed value and p-value. If computed value is more, p-value will be small. But if computed value is small, p-value will be large. And you are comparing just with 0.05. So R, everything will give you a software, R will give you p-value. You just need to look at whether this is less than 0.05 or more than. If it is less, it is going into rejection region. If it is more, it is going into acceptance region. That's all. That's the concept of p-value. Now, after the concept of p-value, certain basics I have already given. We move on to what do you mean by parametric test. Now, there are, let's say you give me some data. Yesterday, some of the participants were saying, I have data regarding to this, I have data related to this. You give me some data. And your problem is, your objective is there, you want to test or you want to compare two different populations, or maybe there is a benchmark which I want to say mean IQ of this population is 100 or something, right? So we use parametric test under certain situation. What are the situations? Parametric tests are applicable to the situation when your data follows normal distribution. That means if you look at the shape of the histogram must look like this. It should be symmetrical. Then we say that it is following a normal distribution. Everybody knows how to draw histogram. So if the shape of the histogram is more or less symmetrical, we say that data comes from normal distribution. Observation must be independent. And the important point is hypothesis must involve population parameters. That means H naught, mu will be equal to mu naught, sigma square will be equal to sigma square, sigma naught square, or something like that. Or mu1 is equal to mu2. It must involve H naught and H1. They should involve population parameters. If these three conditions are satisfied, that your data is coming from normal distribution, it is independent, and your hypothesis is concerning about mean, variance, or proportion, they are the parameters, then we apply parametric test. The question is how to check the normality of the data. There are different methods. One of them is histogram. So how to check the normality of the data? So there are three graphical procedures, and today in the practical example, I'll discuss all of them one by one. One is called histogram. So I'll take up some data and look at the shape of the histogram. If shape of the histogram is almost symmetrical, I'll say data is coming from a normal distribution. And then another plot will be box and whisker plot, which I'll also discuss today. Give you the practical example. But the third and the most important graphical procedures to check the normality of the data is normal quantile plot. That is called QQ plot. That is called QQ plot. QQ plot is called normal quantile plot. Right? So we will discuss all the three graphical procedures today. Now, then there are exact methods of computation, whether the data is coming from a normal distribution or not. And these are the three important tests. They are known as non-parametric test. One of the important tests is called KS test, which is called Kolmogorov-Smirnov test. Another one is called Spirovic test. Another is called Anderson-Darling test. So we will also make use of these tests today. In SPSS, Kolmogorov-Smirnov test is difficult. Sorry, in R, Kolmogorov-Smirnov test is difficult to compute. So I'll give you the demo of Spirovic and Anderson-Darling. They serve the same purpose. So we'll draw these graphics today and also look at how to check the normality of the data by going through the exact test also. These are called exact test, Spirovic and Anderson-Darling. For example, let's look at the shape of this histogram. Now, how to read the histogram? Very important. Whatever is your highest bar, this is the highest bar. You drop a line on the x-axis and then see how many bars are there on the left-hand side and how many bars there on the right-hand side. Now, how many bars are there on the left-hand side? 1, 2, 3. But how many bars there are on the right-hand side? Maybe 8 or 10. That means it is not symmetrical. It is not symmetrical. If this would have been symmetrical, this is a normal curve. Actually, I have drawn the normal curve. All the bars, they should have been within this curve. But you can see some of them are outside. If some of them are outside, you will say the data is not coming from normal distribution. So with the shape of the histogram, you can check. one graph. Another is box plot. Now, what do you mean by today we'll draw the box plot also? I just want to ask one question. Have the box plot been covered in the class or not? By someone? Graphical procedure in R? Yes, please. This box plot has been covered or not in the class? Any participant can answer, please.
Yes, sir.
Okay. So you know then box plot, right? So this is the lower end of the box. This is the upper end of the box. You just have to look at the median. If median would have been right there in the center, let's say median is right there in the center of the box, then your data will follow normal distribution, right? Your data will follow normal distribution. So you can look at the shape of the histogram. You can look at the median line in the box plot. But here you can see that median is not there in the center. That means data does not follow normal distribution. The important graph is QQ plot. And today we'll draw it. This is called QQ plot. It's the same data of some patients, which I have drawn the histogram. For the same data, I have drawn box plot. For the same data, I have drawn the QQ plot. This is a normal line, and this is the quantiles of my data. So if there are deviations here, there are deviations. If my data would have followed normal distribution, all these dots, they should have been on this line. They should have been on this line. Okay. So these are the three important graphs which I mentioned, like histogram, box plot, normal quantile plot, to check the normality of the data. All right. Now, in statistics, basically, there are parametric tests. And parametric tests are available for two types of sample sizes. When your sample size is large, we generally use Z statistics. When your sample size is small, we use T statistics. Right? Now, question is, what do you mean by small sample? Now, it doesn't mean that I fix some number, that it will be a small sample and this will be large sample. No, not like that. Depending upon the population, we have to look into what should be the reasonable small sample size. What is the large sample size? But generally, most of the time, if your sample size is below 30, it is considered to be a small sample. I will tell you the reason. And if your sample size is more than 30, it is generally considered to be a larger sample. Right? Now, there are parallel Z tests for large samples and T test. They test the same thing. For example, single population mean, single population mean. Difference of two population means, difference of two population means. They generally test the same thing. Depending upon if it is large, we apply Z test. If it is small, we apply T test. But with convention here, we try to understand. Actually, the T test approaches to Z test. Please listen to me carefully. Your T test approaches to Z test when your sample size becomes large. That means, what does this mean? That means T test can be used for small samples. And when sample size becomes large, it will approach to Z test. Whether you apply Z test or T test, you will get the same result. So why to unnecessarily compute then Z statistics? Because T test can be used for small sample. It can also be used for large samples. So we will study only the T test. We will study only the T test. Now, where to apply T test? I'll take up one example. Yesterday, we have computed the correlation coefficient, and I said that correlation coefficient is coming out to be significant. That was also tested by T test. Right? So T test generally is used for testing correlation coefficient. It can also be used for testing a population mean, difference of two population means, before and after situation. So I'll take up one example to clarify. Let me take up this example. Where to use one sample T test. One sample T test to be used if there is some benchmark, there is some standard value. and there is only one phenomena or one parameter, like height, or it could be weight, or it could be BMI, or it could be IQ, whatever. And you want to test against a certain fixed value, which is given to you. For example, here claim is that the mean weight of this population is likely to be 100. So I'm referring to mean, framing the null hypothesis, mu will be equal to 60. Alternative will be it is not equal to 60. I don't know what will happen in the population. So there, why it is called one sample? Because I'll take only one sample of weight from the population. If population is, let's say, having 20,000 people, and I want to take a sample of size 200. So I'll take 200 people and note down their weights. So I'm referring to only one phenomena or one variable. That's why it is called one sample t-test. And there must be some standard value to test. If that is the problem, because in many of the experimental situation, we have a standard value. For example, systolic blood pressure, there is a standard value. Diastolic blood pressure, there is a standard value. Mean arterial pressure, there is a standard value. Hemoglobin, there is a standard value, right? So if there is certain standard value we want to test, use one sample t-test, provided, very important, your data must come from normal distribution. You must check the normality of the data first. Very, very important. Then t-test is also used for, does the mean weight differs in, does the mean weight in two regions differ significantly? Let's say there are West Bengal people and people from Assam. Somebody is interested to see that the mean weight of these two different populations, they are almost same in certain age group, say age group between 40 to 50 years of people, let's say, or maybe those children who are below 5 years, anything. I want to compare mean weight in these two regions. So I take one sample from West Bengal, one sample from Assam. Let's say there are 500 observations from West Bengal, 600 observations from Assam, and I want to compare them. These two are independent populations, and I am referring to two different populations. So I'll be using independent t-test, or sometimes also called unpaired t-test, or simply called t-test, or sometimes also called student t-test, right? So my hypothesis will be if mu1 is equal to mu2. Mu1 means this is the weight of the people from West Bengal. These are the weight of the people from Assam. If they are equal, that means the weights are almost equal. Any region you, but if alternative is they may not be equal. They could be Assam may be more, or maybe West Bengal could be more. It can happen. But these are two independent populations, so we use independent t-test. Remember, t-test can compare maximum two groups or maximum two populations. Suppose there is a third population. Let's say I want to compare Assam, West Bengal, and Chhattisgarh. I cannot apply t-test because t-test is applicable only for comparison of two groups, not more than two. That's a restriction of t. If there are 3, 4, 5, then the extension of t-test is called one-way ANOVA, where you can test k number of populations. Mu1 is equal to mu2 is equal to mu3 is equal to mu k. That's one-way ANOVA, which we'll discuss today. Third situation, medicine, whether the medicine is effective in controlling blood pressure or not. So patients are coming to the doctor, right? Now doctor note down their blood pressures. They are suffering from low BP problem. Now doctor give them medicine. It's the same patients. Call the same patients after 2 months. So one value will be before giving the medicine of the blood pressure. Another after 2 months will be of the same patients, after giving the medicine. They are present in pairs, right? And suppose I look at the difference y minus x for each person, and this difference for each person is 0. If the difference is 0, what you will expect? Do you think the medicine is effective? Medicine doesn't have any effect. Otherwise, there should have been some change from before to after. But if there is no change, the differences are 0. That means the medicine is not effective at all. Hopefully, you follow my point. So it's not independent t-test. Observations, it's the same person before and after. Not like Assam and West Bengal. It's the same person before and after. If that is the situation, then we use what is called paired t-test. Then we use what is called paired t-test. Okay? Yeah. So hopefully this and in paired t-test, we make the hypothesis that mu d is equal to 0. What do you mean by mu d is equal to mu d? Mu d stands for mean difference. Mean difference is based on these differences. That mean difference is equal to 0. If I accept the hypothesis that mean difference is 0, that means your medicine is not effective at all. It has to get rejected. Now, even if I say rejected, then I need to check whether it is less than 0 or it is more than 0. Depending upon the situation, it can have worse effect or it can have a better effect, right? So this is called paired t-test. So one sample t-test, independent t-test, paired t-test. This is the formula for one sample t-test. Under H0, we are testing mu is equal to mu naught. And from the given observation of sample of size n, I'll compute x bar, I'll compute the variance, and t will be given by this formula. You will not have to remember the formula, R will give you. But only thing is which you have to remember is that it will t value is a computed value will be given. Now x bar is known to you from the sample observation. Under H0, mu will be equal to mu naught. That is also known. Sample variance you can compute. N is the number of observations. And this is having t distribution with n minus 1 degrees of freedom. How to compute this Sx square? This is the formula. Now, what are these degrees of freedom? Remember, degrees of freedom is generally 1 less than the number of observations. Of course, in many statistical tests, it could be n minus 2 also. For example, in testing of correlation, the degrees of freedom for t is n minus 2, not t minus 1. But for one sample t-test, two sample t-test, degrees of freedom depends upon the number of observations. So you can write down the definition for degrees of freedom, please. If you are interested, you can write down the definition of degrees of freedom. Degrees of freedom are nothing but, you can write down, please. Degrees of freedom are nothing but the number of independent observations. The number of independent observations minus 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 the number of restrictions. Degrees of freedom are nothing but the number of independent observations which form the statistic, minus the number of restrictions. Now, why there are x bar is based on n number of observations. Sx square is based on n number of observations, but there is one restriction. What is that restriction? Restriction is that we are subtracting x bar from each observation. x1 minus x bar, x2 minus x bar, x3 minus x bar. So because of one restriction, the degrees of freedom are n minus 1. So just listen to me. Degrees of freedom are nothing but the number of independent observations which form FORM, which form the statistic, minus 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 the number of restrictions. That's why the degrees of freedom is n minus 1. So R will compute these statistics. From the given data, it will compute x bar. Sx square from this, n is known to you, sample size. Under H0, mu is equal to mu naught. So it will give you the value of t, and we know the graph of t, and p value will be computed. And you just have to see p. If p is less than alpha, reject H0. P more than alpha, accept H0. Right? So p value less than alpha, reject H0. Similarly, for independent t-test, there is a formula. Yes, please.
Sir, can you just conceptually explain degrees of freedom? What actually it implies?
Yeah. Okay. Degrees of freedom basically implies that, let's say I'm standing here and two people are very close to me, and somebody give me this task that you have to do hand exercise, hand uplifting, hand sidewise. So what will happen actually? There will be no freedom because there are two people or there are two walls on the side. I cannot do it freely. Yes or no? I cannot do the exercise freely.
Yes,
Yes.
sir.
For
Yes.
every statistics to work out, there must be sufficient number of degrees of freedom. There must be sufficient number of, that means there must be sufficient space, sufficient number of degrees of freedom so that you can test your hypothesis. Let's say your hypotheses are 0. If your degrees of freedom are 0, no test is applicable. No test is applicable. So you should have sufficient number of degrees of freedom to test any hypothesis. So it will give you a freedom actually. It will give you a freedom whether your test will be valid or it won't be valid. That is the idea of degrees of freedom. So it's nothing but the number of independent observations which form the statistics minus the number of restrictions, right? So that's why we call this as degrees of freedom. Is this clear?
Okay.
All right. Similarly, there is an independent t-test. Independent t-test is also called student t-test or two-sample t-test. Two-sample means there will be two samples, one from Assam, one from West Bengal. Let's say there are two types of groups. One group is put on pizza diet, another group is put on normal diet, and they have been given diet for 1 week, and after 1 week their weight gain have been monitored, and hypothesis is that weight gain due to pizza diet is same as weight gain due to normal diet. That's a hypothesis. Or you can say mu1 is equal to mu2. So if you accept this hypothesis, so whether you take pizza, whether you take normal diet, your weights are not going to increase. But if you reject the hypothesis, then obviously I need to see which results in more weight gain, either pizza diet or normal diet. So it's a two independent samples. That's why this is called independent t-test. There is a formula to compute t-test. It will also give you the t-value, but you will have to see t-value, p-value mainly. And p-value, if it is less than 0.05, reject. What will be H0? Under H0, mu1 will be equal to mu2. That means pizza diet and normal diet, they are same. And results into same weight gain. That's your null hypothesis. So this is called independent t-test. Similarly, for paired t-test. For paired t-test, we are looking at the difference is 0 or not. So one is before giving the treatment, yi values. Another is after giving the treatment, xi. Sorry, one is before giving is xi, after giving is yi. You look at compute these differences. If all differences are pre and post. Somebody was asking yesterday, what should I do if there is a pre and post? So if there are pre scores, there are post scores. That means you want to see what is the improvement. You must apply pair t-test. And this is the formula to compute pair t-test, because entire thing can be converted in terms of di values. D1 will be y1 minus x1, it will be a single value. D2 will be y2 minus x2, it will be a single value. And for those di values, you compute d bar, you compute standard deviation of the differences, and this will be t is nothing but d bar divided by standard deviation of the differences divided by under root n. Apply this formula. This is again having t distribution with n minus 1 degrees of freedom, right? So this is called pair t-test. So remember, one sample t-test, two sample t-test or independent t-test or pair t-test, they are applicable only when your data comes from normal distribution. That's a basic assumption. Now for t-test, I have completed all the basics. Now I'll move on to the practical time. Otherwise, you will forget. Once we start one-way ANOVA, two-way ANOVA, these things may skip out of the mind. So I'll give you the practical demo first, and then we'll move on to one-way ANOVA and two-way ANOVA later on. If you still have any questions, related to the theoretical part, what I have considered, you are most welcome to ask. Yes, please. Anything which is not clear. Yes, please. No question?
I think no, sir.
Okay. So if you are clear about this, then I'll give you a practical demonstration. Let's see how many participants are right here. 27. Very good. So you have 27 number. So let me give you the practical demo of whatever we have considered. I'll check the normality of the data, the procedure which I have shown you using R, and we also check the apply these tests, one sample t-test, two sample t-test, and pair t-test. Okay, let me open the file. This is a Vishwabharati folder, and these are the all programs. Open the R Studio file. Okay. Now, hopefully, can you see the desktop now? Is the screen is visible?
Sir, yes, sir.
Okay. Now you see this. You first of all, you go to your own directory. That is your main thing. So you set your own directory and you are into your own directory. That's called Vishwabharati. Now, correlation, etc. we have already covered. I'll not go again and again. We straight away move on to multiple regression we have done. How to check the normality of the data. So here is how to check the normality of the data. Now, normality of the data, there are three graphical procedures, right? And also there are three exact tests: Kolmogorov-Smirnov test, Spiro-Wilk test, Anderson-Darling test. But in R, we will study only two, Spiro-Wilk and Anderson-Darling. But there is another way to check the normality of the data. That is through skewness and kurtosis. Hopefully somebody must have taught you skewness and kurtosis. If your data is not symmetrical, it could be positively skewed, it could be negatively skewed. Similarly, kurtosis measures the peakedness of the curve, how peak it is, how flat it is. And roughly, please remember, if the value of skewness and kurtosis, both, if the value of skewness and kurtosis lies between -2 to +2. Let me just repeat. R will give you the value of skewness. R will also give you the value of kurtosis for any given data. What I'm saying, that if the skewness value and kurtosis value, both of them lie between -2 to +2, then your data is approximately normally distributed. You follow what I'm saying? But if any one of them, either skewness is below -2 or above +2, or kurtosis is below -2 or above +2, then the data is not normally distributed. Yes, please. You follow this part? Hello?
Yes, sir.
Yeah. Please, आप थोड़ा line पे रहिए, because I will be asking some questions now. So first of all, we will go through checking through skewness and kurtosis. For to check the through skewness and kurtosis, how to check the normality of the data through skewness and kurtosis, there is one important package which you need to install. That package is called Movements. You can also install the package from here. This is the list of packages, or you can go to Tools and go to Install Packages, and you can write Movements here and then click on to install. Then that package will be loaded. Or you can manually also load install.packages Movements, and then take this package of Movements to the library so that it is executable. So I'll take install. It will take maybe some fraction of time. So it is installing the Movements package. So it's done, and then you take this to the library of the R. So it is in the library of R. So whatever, for example, skewness and kurtosis, they are based on Movements. So it requires that package. So let me take some data. Suppose this is X data. It's a data. Now I will check what is the skewness and kurtosis of this data. Whether this question here is whether this X data, the values which we have, whether they are having normal distribution or not. This is what we want, right? So this is your X. All the values are there in X. I'll compute the skewness of X. I'll also compute the kurtosis of X. Now, if skewness lies between -2 to +2, okay. If kurtosis also lies between -2 to +2, it's fine that X data is normally distributed. You can go ahead with any test. But suppose either skewness or kurtosis or both are outside the limits of -2 to +2. That means the data is not normally distributed. And parametric tests are applicable only for normally distributed data. So let me first of all check the skewness. So skewness value is 1.06752. That means it is between -2 to +2. It's fine. Skewness is okay. But I have to see both of them simultaneously. Look at the kurtosis. Kurtosis value is coming out to be 3.06. Now there is a problem. Although skewness was between -2 to +2, but skewness is beyond 2. It's 3 point something. What do you think? Yes, aap bataiye. Do you think the data is normally distributed?
Not
Yes,
normal, sir.
Yeah, it is not normally distributed. So I have checked through skewness and kurtosis. Okay, that is one part. Another way I have told you to draw histogram. Now you run histogram of X, his text. You look at the shape of the histogram. This is the shape of the histogram. And how to read the shape of the histogram? I draw a line from the highest bar. There is only one bar on the left hand side, but there are 1, 2, 3 bars on the right hand side. Do you think it is symmetrical? Yes, please.
No, sir.
It is not symmetrical. If it is not symmetrical, that means data is not following a
Normalities.
normal distribution. All right. That means the same thing was given by skewness and kurtosis, and histogram is also giving you the same picture, that data is not normally distributed. Then you can also look at the box plot. So this is the box plot. If you look at the shape of the box plot and look at the median, do you think the median is there in the center of the box?
No, sir. It is below, sir.
It is below. If it is below, it is basically positively skewed. If this would have been here, it is negatively skewed. If right there in the center, then it is symmetrical. So obviously data is not normally distributed, right? So that is a box plot. If median is there, then this would have been right there in the center. There is no need to check. Your data is normal, no problem at all. Okay. Another is QQ plot, quantile plot. And this is the command, QQ norm X. So look at this. This is the data. These are the quantiles of your data. What is a quantile? Quantile is basically called fraction. For example, how do we compute median? We arrange the data in order. Look at the middlemost value. That will be your median. Yes or no? Yes, please.
Yes, sir.
Now, median is halfway. Similarly, there are quartiles. If there are 100 observations, I arrange the data in order. Then I compute Q1 and Q3. What is Q1? Q1 means the first quartile of the data. First quartile means 25th observation. So if you arrange the data in order, your whatever is 25th value, that is the value of Q1. And with 75th value is value of Q3. And in box plot, the lower end is placed against Q1, upper end is placed against Q3, and box is between Q1 and Q3. But that is for 25th, 75th. Suppose somebody looking into fraction, I cannot compute fraction, then these are called quantiles. For example, if there are 30 observations, you arrange 30 observations in order from the lowest to the highest. Then obviously, the first observation will form 1/30th part of the data. Yes or no? Yes, please.
Yes, sir.
So 1/30th means 1/30.033. So it's a fraction. So it computes, then second observation will form 2/30th part of the data. Third will form 3 by 30th part of the data, and so on. So these are quantiles. These are dots, line are quantiles of your data. Then if you draw the QQ line, they are the quantiles of the normal. So if I draw the quantile line, they are the quantiles of the normal. If your data would have been normal, all these points, they should have been on this line. Do you think all the points are there on this line? Yes or no?
Away, sir.
They are away. Only few points very close, otherwise they are away. So what does this mean? This simply says that the data is not following a, yes
normal
please, data
distribution.
is not following a normal distribution. So whether you look at skewness curtices, whether you look at histogram, box plot, quantile plot, everything is giving you the same information. Is that okay?
Yes, sir.
Good. So I'm just closing this. Now we go for the checking of the normality with the test also. Spirovic test and Anderson-Darling test. So to check the normality, of the data, I need to install one package, and that is called normal test. Nor test means normality test. So install this package first. It will take fraction of seconds. It is installing. Now it has been installed. Take this to the library. So now we are. Then this is called Spirovic test. X data is already with us. So let's check this. Now you can write down the hypothesis now. Now you understand very much what do you mean by hypothesis. Your H0 is data follows normal distribution, or data comes from normal distribution. That is your H0. Write down the alternative also, please. Data does not follow normal distribution, or data does not come from normal distribution. That is your alternative. So Spirovic test, AD test is called Anderson-Darling test. Both of them will give you p-value. You just need to look at alpha is 0.05. If your p-value is less than 0.05, reject H0. That means data is not coming from it. But if this is greater than 0.05, then accept H0, that data is coming from a normal distribution. Yes, please. Is that clear?
Can you come again, sir? P-value, normally when it is less than 0.05, we
Reject H0.
say it is significant. I mean,
Yeah, it is
normally
significant. Significant means rejection of H0. What is H0? Data comes from normal distribution. So it will be rejected. That means data doesn't follow normal distribution. Alternative will be accepted. So let's look at Spirovic test result and look at the p-value. So it says Spirovic normality test. This is the test statistics. This is a p-value. What is the p-value here? Can you read, please?
0.015.
Is it less than 0.05 or more than?
Slight less than, sir.
Less than. So what was our H0? I have asked you to note it down in pen and pencil. What was H0?
Rejected.
So H0 is rejected. What was H0? I am asking what was H0? Data follows normal distribution.
Test.
Right?
Yes.
Data follows normal distribution. Now it has been rejected. That means data does not follow basically normal distribution. Is that okay? That's the answer now. What is the answer of this? That means data does not follow normal distribution. It fails the test of normality because p-value is less than 0.05. Yes, please. Is that okay?
Yes, sir.
All right. Now you see the similarity. Histogram give you the same result. Box plot, same result. Quantile plot, same result. Skewness kurtosis, same result. Spirovic test, same result. Because it's the same data. Let's apply Anderson-Darling also and see the result. This is the result of Anderson-Darling. What is the p-value here? Yes, please.
0.008.
Is it less than 0.05 or more than?
Yeah, less than.
Less than. Less than means H0 will be rejected. H0 was data is coming from a normal distribution. It has been rejected. That means your data does not follow normal distribution. So all the test, all the graphs, everything, skewness, kurtosis including, giving you the same information. Is that okay?
Yes, sir. But
So this
depending
is-
upon the test that we can execute, sir, the p-values are different, no, sir?
Yeah, p-values will differ because there are different tests. But as far as data is concerned, you will get the same answer. Whether you apply Anderson-Darling, whether you apply Spirovilk, almost p-value may little bit here and there, but result will be same. Either
Will
H0
there be a case when
yeah, it can happen.
this
It can,
Sapiro
yeah,
test
it
gives
can,
you
no.
another
Listen to me.
result and the other one?
It can sometimes happen when there is a borderline case. Sometimes approximately normally distributed. In that case, sometimes there will be here and there. In that case, you must follow Spirovilk test. That is more powerful than Anderson-Darling test.
Okay, sir.
Okay. Now, because I have taken some random data, you see, I have just taken some random data, some observations. But suppose I take data from normal distribution, then check what is happening. Suppose I take data from some normal distribution. Now, and check the same thing, everything I'll check. So how to take a data from normal distribution? There is a command in R. Let's say height data. I'll put this as height, and I'll take 500 people. So it will generate a 500 observations, and whose mean height is going to be 168. Mean height is 168 centimeter with a standard deviation of 3. So I have to specify that generate a random sample. R norm. R norm means random sample from normal distribution. You follow my point? R norm stands for random sample from normal distribution. Is that okay?
Okay, sir.
And you specify, if I take n 100, it will generate 100 observations. If you compute the mean of those 100, you will get the value 168. If you compute
Sir,
the
it
standard
will
deviation,
generate the data from the R memory, sir.
it will automatically generate the data from normal distribution.
But
Normal distribution is
where is
critical.
that data stored, sir? Is it in the memory of the R, sir?
Yeah, it will come to the height. I'm just giving this variable name as height. So it will be, you will get all the 500 observations. I'll show
But
you.
where from will we get the data from? From R memory, sir? Is it pre-stored in the R software?
No. Just listen to me. For every package, there is an inbuilt program of random numbers. Inbuilt program. And once we execute this command, which is called rnorm, that particular, you can say, module will be activated, and it will automatically generate a random sample from that distribution. Similarly, you can generate random number from chi-square distribution, random number from F distribution, random number from binomial distribution. For example, if I want to let's say generate random sample from binomial, I'll write R binom. If from Poisson, I'll write R Pois, P-O-I-S. So there are different commands. I'm taking normal. So I'm writing R norm, that you take a sample of, you generate a random sample from normal distribution, whose mean will be 168 and standard deviation will be 3. What does this mean? That if it will generate 500 observation, if you compute the mean height, that will come out to be closer to 168. If you compute the standard deviation of those 500, it will be closer to 3. I can show you. This is what it means. You follow my point?
Yes, sir.
So let me generate. So it has been generated. They are stored. Let me take height. So these are all 500 observations. You see, these are all 500 observations which have been generated. Right? And if you take the mean height, that's a mean height, because we have already given that mean should be around 168. So let me put this as H-E-I-T-H-T, mean height. Okay. Let me check what is the value. Mean height. So it's 168 approximately. Yes or no?
Yes, sir.
Because I have given the instruction that you generate a random sample from normal distribution whose mean should be around 168 and SD should be around 3. Let's check SD also. SD of height. This is what we mean by random sample. SD of height. How much is this? Yes, please.
3.028.
So that means it's close. So that means you are getting a random sample from a normal distribution. Now I know that this sample is already following a normal distribution. Yes or no?
Yes, sir.
So its graph should be, if I look at the histogram should be symmetrical. Yes or no?
Yes, absolutely, sir.
And in box plot, median line should be there in the center.
Should be in the center.
And quantile plot, all the points they should be on the line.
Q
Yes.
lines.
So let's see. Let's check this histogram of height. Now you see it's almost symmetrical. Yes or no?
Yes.
It's almost symmetrical. Let's look at box plot also. There is no box plot here. Let me put the box plot. Box plot of height. The box plot also. Run this. So it's almost in the center. Yes.
It is in the center.
Because data is coming from a normal distribution. That's why all the parameters are intact. Then you can also look into quantile plot. This is a quantile plot. And if you draw the line, you can see this. The points are almost, I have put this up, almost on the line. Yes or no? Yes? Almost on the line. Most
Yes,
maximum points. Out of 500, maybe one or 2 point here, 1 point here. Otherwise, 497 points, they are very, very close. Is that okay?
Okay, sir.
What does this mean? That this data is following a, yes, please. This data is following a
Normal distribution.
normal distribution. Good.
But
Now,
sir,
what do you,
but sir, its kurtosis value is more than 2. I have find it is coming 2.82.
let me look into skewness. Skewness of height. And also I'll go through kurtosis. Kurtosis of height. Okay. Compute the skewness in kurtosis. It's 0.03. Kurtosis is 2.84. Right? You are saying this thing?
Yes, sir.
Why it is coming? Because you are taking a sample of size 500. Let's say I take a sample of size more than that. Suppose I take a sample of size, say 5,000. Let's say I take a sample of size 5,000 and again compute skewness now. Compute skewness, compute kurtosis. It's 2.99. Still it is more, right? Because skewness and kurtosis, they are just the rule of thumb. It's not the exact. Generally we avoid. Let me tell you. Generally we do not go for the normality test based on skewness and kurtosis. That's why I didn't put right there in the slide. I say either you follow graphical procedure or you follow the exact test. Because they are just rule of thumb. Rule of thumb means sometimes they may not give you the correct interpretation. That's the idea. Of course, if you take a sample of size more than that, then sometimes you will get better results. Let's say I take sample of size this much. And you can see and compute, let's say skewness, kurtosis. So again, it is coming out. It's coming out to be same thing. But anyhow, some extreme values are there. Doesn't matter. So they are just rule of thumb. Generally, we don't go for skewness and kurtosis. It is just for your knowledge. That if you don't know how to plot histogram or a box plot, you can just look at skewness and kurtosis. Their values between -1 to -2 to +2. You can think this is approximately normally distributed. Okay, but they are not the better measures of. They are not good measures of. Looking at the normality test. Now we look at, we have seen AD test of height. AD test of height. What is the p-value here? Yes, please, p-value. Hello. Hello.
Yes, sir.
Yes, sir.
What is the p-value here of Anderson-Darling test?
0.33.
Is it less than 0.05 or more than?
0.33.
No. Is it less than 0.0?
More than.
More than.
More than.
So what?
More-
what was
more
the
than.
More than means what?
Hypothesis will be accepted and our assumption will be rejected.
No. Hypothesis accepted means what?
Means our assumption will accepted, that is it is follow normal distribution.
Yeah, it is following a normal distribution. Again applies Spiroville can test.
Salam, Sada, sir.
Pardon? Pardon?
Excuse me,
Say,
sir. I'm
it says-
sorry. Yeah, it's okay, sir.
See, let me just reduce the sample size, because for Spiroville it says that your sample size between 500 and something. So run this, and it says the sample size must be between 3 to 5,000. So I've taken 500. Now you run Spiroville. Again, p-value is how much now? Yes, please. Hello.
0.67.
So again, hypothesis will be accepted.
Accepted.
And when the hypothesis will be accepted, your data is following a normal distribution. So histogram, box plot, quantile plot, Spiroville, Anderson-Darling, giving you the same result. Is that okay?
Okay.
So this is how to check the normality of the data. Now, I think, can we go for e-test, etc., or after the break? What do you suggest?
Sir, let's have a rest for some time, sir.
Yeah.
Maybe we can come
Let's
back.
take a
early.
break of almost 20 minutes. So I'll be back at 5:15. Will that be okay? 5:15?
Okay.
So that we can finish around 7 or before 7.
Yes, sir.
So I'll be back in 20 minutes. Please don't go anywhere. And I request not to go anywhere. And just be with me. I'll be back in 20 minutes. Be here at 5:15. 5:15 sharp. I'll be discussing all t values. There are inbuilt data sets in R. How to find out those data sets, I will also show you. All
Okay,
right.
sir.
I'll be back in 20 minutes.